So thank you very much. I'm Tamás Király, the first chair. I think everyone is muted, apart from me and the speaker. And so if you have a question during the talk, then please use the chat. And after the talk, there will be a Q&A session where you can raise your hand and I will unmute you and you can ask the questions. So our first speaker is Yuni Iwamasa from Kyoto. And, the talk is about a combinatorial algorithm for computing the rank of a generic partition matrix. So let us start. Yuni, please start the talk.
Yeah. Can you hear me?
Yes.
Yes, okay, thank you. I'm Yuni Iwamasa. Thank you for my introduction. And I'm Yuni Iwamasa from Kyoto University. And today I'll talk about rank computation of a matrix having variables. And this is joint work with Hiroshi Hirai. Okay, so let's start. And many of matching type combinatorial optimization program can be formulated as the rank computation of a matrix having variables. The most typical example is maximum bipartite matching. And from the bipartite graph G, we naturally construct a matrix A having variables, and in which if there is an H between I and J in G, then the corresponding ij's entry of A is xij. And if there is no H between I and J here, then the corresponding entry is 0. And this is called the Edmans matrix. And it is well known that the size of maximum matching is equal to the rank of this matrix. And so this is an algebraic formulation of maximum bipartite matching. And here, in partitioning A into one by one submatrices like this, then each submatrix have at most one variable, and the different submatrices have different variables. And by abstracting this structure, we consider a 2x2 type generic partitioned matrix named 2x2 type GPM introduced by Iwata and Murata. And this is a matrix A with the size of 2 mu by 2 nu matrix. And when we partition A into 2x2 matrix like this, then the alpha beta blocks, alpha beta submatrix consists of a 2x2 matrix A alpha beta over F and a variable X alpha beta. So here we know that the different submatrices have different variables like this. And here it is known that there exists a minimax theorem on its rank. And it says that the rank of A is equal to the minimization of some kind of optimization problems over vector spaces. And in this talk, we'll consider the rank computation of a 2x2 type GPM. And actually, there already exists polynomial time algorithms for our problem by solving non-commutative Edmans problem, which we will see later.
Just a question from the chat by Daniel. We mean the maximum rank here, right?
Yes. So the rank is a maximum size of the submatrices having a determinant. So I mean, so this is maximum.
Okay.
Okay, thank you. And okay, so there exists a polynomial time algorithm by solving non-commutative Edmans problem. That the existing algorithms are analytical or complicated or slow. So in this talk, we develop a combinatorial and a relatively simple and a faster algorithm for our problem. And this is our main result. Okay, so before introducing our result, let me introduce related problems and results. Okay, so Edmans problem is a problem of computing the rank of a linear symbolic matrix A, represented as the sum of AI and Xi, sum of AI Xi, where AI is n by n matrix over F and Xi is a variable. As we can easily see that, so Edmans problem can formulate our problem, and it is also known that Edmans problem can formulate many of matching type combinatorial optimization problems, such as maximum bipartite matching, linear matrix intersection, maximum matching, and linear measured parity. And it is known that there exists a randomized polynomial time algorithm for Edmans problem if the size of F is sufficiently large. But it is open whether there exists a deterministic polynomial time algorithms, and also open whether the minimax theorem on its rank. And there are important open problems, not only in combinatorial optimization, but also in theoretical computer science, such as circuit complexity theory.
So there's another question. Is your matrix symbolic?
Yes, symbolic matrix.
Yeah.
Thanks. So matrix is over field, the relational function field. Okay, thank you. And then non-commutative Edmans problem is the non-commutative version of Edmans problem, as its name states. And the problem description is the same as the Edmans problem, but in non-commutative setting, variables are supposed to be non-commutative. That is, xi, xj is different from xj, xi. And so for such a matrix A, we can define the rank concept similarly by inner rank of a matrix over field, over link. And so we call it NC rank or non-commutative rank in this setting. So summarizing, the non-commutative Edmans problem is the problem of computing the NC rank of this symbolic matrix. And non-commutative Edmans problem has a minimax theorem, and while Edmans problem doesn't have. And surprisingly, there exists deterministic polynomial time algorithm for non-commutative Edmans problem. So there are three kinds of polynomial time algorithms which were developed independently. But so they are analytical or complicated or slow. And so, yeah, so such algorithms are analytical and so, yeah. And anyway, so by their results, so we can solve Edmans problem for matrix A such that its rank and the initial rank coincide in polynomial time by solving non-commutative Edmans problem for A. So in general, the rank is strictly smaller than initial rank, but there are several classes of matrices such that its rank and initial rank coincides. And it is known that 2x2 type GPM is included in this class. So we can say that we can compute the rank of 2x2 type GPM in polynomial time by solving non-commutative Edmans problem. So, but as I mentioned, so the existing algorithms are analytical or complicated or slow. So in this talk, we develop a new algorithm for the rank computation of this matrix. Okay, so our proposed algorithm is inspired by an augmenting path type algorithm on vector spaces introduced by Iwamasa, Xiao, Sabram, Yang. Sorry. And this is an algorithm for a non-commutative Edmans problem. And the differences are as follows. And in IQS algorithm, we find an augmenting path for an arbitrary matrix. But on the other hand, in our algorithm, we find an augmenting path for a matching for a 2x2 type GPM, which is introduced in this paper. And in IQS algorithm, we have to conduct a blow-up operation to the matrix in the augmentation, and which makes the algorithm complicated. But in our algorithm, we don't have to do it. So algorithm is simpler than IQS algorithm. Okay, so let me define the matching for a 2x2 type GPM. From a matrix A, 2x2 GPM, here, we naturally construct a bipartite graph G, where the left side vertices are corresponding to the row indices of blocks, and the right side vertices are corresponding to the column indices of blocks. And there is an edge between alpha and beta in G, if and only if the corresponding submatrices A alpha beta is non-zero matrix. So an edge is called is said to be rank K if the rank of corresponding submatrices is K. And conversely, from H subset I, we naturally construct the corresponding matrix AI like this. So here there is an edge between, there is an alpha beta is in I if and only if the corresponding sum matrix remains is A alpha beta X alpha beta. And if there is no edge in alpha beta is not in I, then the corresponding sum matrix is 0.
There is a question. So the rank is computed over a finite field F or any field, or?
Oh, here this rank is in the normal the F over F. This, the rank means the rank over F.
Over F. Okay.
And but this the rank of this matrix is computed in the over rational function field Fx.
Mm-hmm.
Okay. Thanks. And we can define the matching. And if an H subset I is a matching, sorry, H subset I is called a matching if by deleting any H alpha beta in I from I, the corresponding the rank of corresponding matrix strictly decreases from the rank of the original matrix AI. So here the rank is over the rational function field. And so we can define a matching concept similarly to 1x1 type GPM. And so for if this matching concept coincides with the bipartite graph of the original meaning, so this is a natural generalization of matching. And we first give the characterization of matching for 2x2 type GPM. H subset I is a matching if and only if I satisfies the following 4 conditions. And the first condition DEC is the condition that for any vertex in G, its degree in I is at most 2. So this means that I forms the disjoint union of a path component and cycle component. And so I is 2H colorable. That is, we can introduce 2 H classes plus H and minus H's so that H plus H are only incident to minus H's and the minus H's are only incident to plus H's. So like this picture. Then the path is a condition of path component. And for any non-isolated path component or any path component with length at least 2 of I, then the both end edges here and here are rank 1. This is a path component, a path condition. And the cycle is the condition on cycle component. And every cycle component of I has both a rank 1 plus H and a rank 1 minus H, like this. This is a cycle condition. And finally, so VL is an algebraic condition. And so VL is a condition that for any alpha in the left side and beta in the right side, there exist 2 distinct one-dimensional vector subspaces named a plus space and a minus space, such that for any H alpha beta, the 2 condition holds. And I'll explain this condition by this toy example here. And now we have a 2.
So let me just clarify, because it maybe was unclear for the question. So F can be any field. It's not necessarily a finite field, right?
Yes, yes, yes.
It can be any field. Okay.
Yes, yes, any field. Yeah, thank you. Okay, now we have 2 spaces, plus space and minus space for each vertex, like this. Oh, sorry. And the first condition is on a rank 1 edge. If alpha beta is a rank 1 plus edge, then the plus spaces of alpha and beta coincides with the left and right kernel of A alpha beta. So in this picture, there are 2 plus rank 1 edges here and here. So the endpoints of each rank 1 plus edges here and here. So the plus spaces of 3 and minus plus spaces of this 3 are determined by the left and right kernel of A33, respectively. And similarly, for if alpha beta is a rank 1 minus H, then the minus spaces of alpha and beta are determined by its kernel. corresponding to the kernel of the corresponding submatrices. And here, so this is on vector space over F. And in this picture, there is one rank 1 edge, and so the minor space of 5 and 4 are determined by its kernel, like this. And the second condition is on basically on the rank 2 edges. And so for any edge alpha beta, the minor space of alpha and plus space of beta are orthogonal to with respect to alpha beta, A alpha beta. So in this picture, the U4 minus must be the orthogonal subspace to V3 plus with respect to this edge.
There is a question. Is this only for path component?
No, any component.
Any component. Okay.
Yeah, thank you. But this is, for example, of path component here. And similarly, V4 plus must be the orthogonal subspace to U4 minus with respect to this edge. So in other words, the such minor space and plus space are uniquely determined by the propagation of V3 plus along this path. Okay. And similarly, the plus space of alpha and the minus space of beta is also are also orthogonal with respect to alpha beta. So this plus space and this minus space are uniquely determined by the propagation of V4 minus along the reverse of this path. So in other words, VL requires that. Okay, so okay, we can determine plus and minus spaces like this. So plus and minus spaces satisfying these two conditions like this. So VL requires that if we determine plus and minus spaces like this, then they are different. This requires VL requires such condition. So this is a VL, the condition VL. And so VL stands for valid labeling, which is vector subspaces like this, vector subspaces satisfying these conditions. Okay. Okay, we also show that for a matching of our 2x2 type GPM, its rank is determined by the combinatorial structure of a H subset I, and easily computed. So the rank of AI is equal to the size of I plus the number of isolated rank 2 edges in I, and which is denoted by R of I here. So by this theorem, we can say that so our problem, so computing rank A, is equivalent to the problem of finding a maximum matching I, where maximum is defined as I is said to be maximum if its rank is maximum among all matchings, or equivalent to its rank is equal to the rank of A. So our problem can be reduced to the problem of finding the maximum matching by this theorem. And by combining Iwata-Murata's minimax theorem and this theorem, our result, we immediately obtain a new minimax theorem that relates a combinatorial value on matching and algebraic value like this. And vector subspaces that attains this identity is called optimality witness of I. So by this corollary, we can say that if there exists an optimal witness of I, then the I is maximum. Okay. So let me introduce an outline of our algorithm. So first, we have a matching at hand here. And if we can find an optimality witness of I, then it means that I is maximum. So we output R of I, the combinatorial value of I, as a rank of A. And otherwise, we can find an augmenting spacewalk for I. So in this case, we can augment a matching. Or in other words, we can find a larger matching I prime satisfying this condition, and update I to this matching, and repeat this procedure. So this is an outline of our algorithm. And
you have 5 minutes left.
Okay. And so now this procedure can be done in order E squared time. E is the number of edges of a bipartite graph. And the number of repeats is clearly bound by its rank. So the running time of our algorithm is this. Okay, so due to time constraint, we can only a very brief introduction of our augmenting procedure. So let me introduce it. And so suppose we now consider the following situation where I draw a bipartite graph and rotate it by 19 degrees to the left in this picture. Okay, suppose that yi let yi be the right kernel of this edge. Okay, and we consider the propagation of yi along this path here. So we obtain, okay, and additionally, suppose yi is not included in the right kernel of this edge here. So we obtain xy, x1, and y2, and x2, and so on, like this. And here we assume that each yi is not included in the right kernel of this dotted edge. And finally, we obtain x3 by the propagation of yi along this path. Okay. And so we obtain a sequence of vector spaces and edges. Yi, this edge, xi, this edge, and so on. Okay. And so further assume that x3 is different from left kernel of this edge. So in this case, we can augment a matching by adding all edges in the path. So indeed, the number of edges increases by 3 here, and the number of isolated rank 2 edges decreases by 2. So R increases by 1. So, and from now we see that this edge subset satisfies VL. And by the condition of the left kernel of this edge is different from x3. Okay, now here we define x3 check by the left kernel of this edge. And so we have they are different by the condition, by the assumption. And now we consider the propagation of x3 check along the reverse path, like this. Then by this assumption and these assumption, we can say that for each vertex, and normal checked space and the normal space, non-checked space are different. So please recall the construction of plus and minus spaces in the condition VL. So this means that the construction of plus and minus spaces is the same as this back propagation and the front propagation. So we can say that these spaces are minus spaces, and these spaces are minus spaces, and let these spaces are plus spaces. And they are different. So we can say that this is a valid labeling of a new edge subset. So we obtain a larger matching now by adding the edges in path. So here we can say that, so if we have an appropriate sequence of vector spaces and edges in the green line, so we can augment a matching. So by abstracting this observation, we introduced an augmenting spacewalk for I. But so due to time constraints, so we can only give a very brief introduction of it. So here, the augmenting spacewalk is the concatenation of outer spacewalks and inner spacewalks, where there are sequences of vector spaces and edges. And this is a diagram, conceptual diagram of augmenting spacewalk. And here, this part is outer spacewalk, and this part is inner spacewalk, and so on. The outer spacewalk are similar to normal alternating paths of bipartite matching, and in the spacewalk goes through connected component containing rank 1 edges like this. And the previous desirable situation is equal to the case where our augmenting spacewalk consists of a single outer spacewalk and it forms a path. Okay, the outline of our augmenting procedure is as follows. First, we have the pair as input, where the I is matching and T is an augmenting spacewalk for I. And for this pair, we apply the order E modifications, where each modification can be done in order E time. Then we obtain another pair, I prime and T prime, and which is in a desirable situation, as I mentioned before. And then we can augment a matching and output a larger matching Geister. This is an outline of our framework, and this can be done in order E squared time. Okay, so this is conclusion. That's it. Thank you for your attention.
Thank you very much. And now it's time for questions, but a short time for questions. So please raise your hand if you have a question. I hope I can see the raised hands in this list. I cannot see raised hands yet.
I have a question, but as a
Okay.
host, I cannot
Yeah.
raise my blue hand, so I'm
Please
not,
go
I'm
ahead.
violating the rules. Sorry. I was wondering if you look at a partition matrix of higher order, not necessarily 2 times 2, what goes wrong in? So I guess is there any hope of extending your argument?
Yeah, so it's a very good question, and okay, so in general, the generic partition matrix is not satisfies this condition. So in general, so generic partition matrix, its rank and MC rank does not equal. And so if there is 2 by 3 blocks, then it can happen. Okay. And we can define the matching concept for this class, generic partition matrix. That's so okay. So if a rank and MC rank, if MC rank is greater than rank, then we have to blow up. We have to conduct a blow up operation to compute the MC rank. So we don't know how to compute rank. Its rank of normal rank GPM. So I don't know how to resolve it.
But is it known if it's hard even for partition matrices? Because I mean it's a special class, right? Even if the 2 ranks don't coincide.
Yeah. And so the rank computation of GPM is equivalent to Edmans problem. So if we can compute the rank of GPM in general GPM, then we can solve Edmans problem in deterministically. So I think it's difficult now.
Okay, thank you.
Okay, Dan Vadush has a question.
Let's see. Yeah, so from the picture, I guess it says that if you could compute this rank for skew symmetric matrices, you would recover the matroid parity. Is that what it is?
Yeah.
But so currently your algorithm does not do this.
Yes, we cannot apply our algorithm to this class.
And that's because there you actually need to compute the non-commutative rank. Is that and that's the issue?
Sorry, non-commutative rank for this?
Yeah, is that the issue? And then you can only compute standard rank, but not non-commutative rank? Or I'm missing something? Where is the difference essentially between what you're doing and what would need to happen to get an algorithm for linear matroid parity? I guess maximum cardinality.
So you mean, okay. So first, so our algorithm cannot apply to this class, and so okay, we can compute the NC rank of this class, but it's not the same as the linear metric party.
So the matrix structure is different, right?
Yes, yes. Okay, so also matrix structure is different. So in this class, so we consider the we consider this formulation, right? But in our algorithm, in our problem, we have this structure, and so the structure are different. So we cannot apply our algorithm to normal Edmans problem.
So the matrices are not 2 by 2; they're just rank 2.
Yes.
Ah, I see. Okay.
Rank 2 means each matrix of over size n by n is rank 2.
I see.
Okay, thank you. So there is no more time for questions. So let me try to unmute all of you, and then we can give a round of applause for the speaker.
Thank you very much.
Okay, I will